2 days ago, NASA released data that changes everything we thought we knew about the edge of our solar system. And I need you to understand something before we go any further. This is not speculation. This is not theory. This is not some clickbait headline designed to get your attention. This is direct measurement from instruments that have traveled farther than any human-made object in history. Actual data, real numbers, observations that we can verify and analyze. Voyager 1 and Voyager 2, the spacecraft many of you watched launch back in 1977, have discovered something that according to our models should not exist. An invisible wall, a barrier of superheated particles waiting at the boundary between our sun's domain and the infinite void beyond. A region where temperatures spike to levels that should be impossible in what we thought was cold, empty space. And here is what is keeping NASA scientists awake at night. After decades of study, after analyzing terabytes of data, after running thousands of simulations, they still have no complete explanation for why it is there. The models work up to a point, then they break down. Something is happening at the edge of our solar system that we do not fully understand. Welcome back to the channel. Let me take you back to where this story begins. September 5th, 1977, Cape Canaveral, Florida. The morning air thick with humidity and anticipation. A crowd of engineers, scientists, and journalists gathered to witness something historic. Voyager 1 sat on the launch pad, a spacecraft roughly the size of a small car, packed with instruments that represented the absolute cutting edge of 1970s technology. Computers less powerful than the phone in your pocket. Cameras that would be considered primitive by today's standards. Communication systems that had never been tested at the distances they would eventually reach. The mission objective was straightforward. Visit Jupiter, visit Saturn, send back pictures, maybe last 5 years if everything went perfectly. Maybe push it to 7 or 8 if they got really lucky. That was 48 years ago, nearly half a century, an entire human lifetime. Voyager 1 is still out there, still transmitting, still sending data back to Earth from 15.8 billion miles away. Let that number sink in for a moment. 15.8 billion miles. If you got in a car right now and drove at highway speed without stopping, it would take you over 28 million years to reach where Voyager 1 is today. The spacecraft is moving at 38,000 miles per hour through a region of space that no human-made object has ever explored. A region we have only theorized about. A region that, until Voyager arrived, existed only in mathematical models and educated guesses. What Voyager found there defies easy explanation. And the more data we receive, the stranger the picture becomes. Between 2012 and 2018, both Voyager spacecraft crossed what scientists call the Heliopause. This is the official boundary where our sun's influence ends and true interstellar space begins. Think of our solar system as a bubble. Inside the bubble, the sun is in charge. Solar wind, solar radiation, solar magnetic fields, all of it dominates. Outside the bubble, you are in the territory of the galaxy itself. Different rules, different forces, different everything. The Heliopause is where that transition happens. And at that precise moment of crossing, at that exact boundary between our cosmic home and the universe beyond, Voyager's instruments recorded something extraordinary. Temperature readings spiked to between 30,000 and 50,000 Kelvin. Now, if you are not familiar with the Kelvin scale, let me translate that into terms that might hit harder. We are talking about 50,000 to 90,000 degrees Fahrenheit. For context, for perspective, for a sense of just how extreme that is, consider this. The surface of our sun, the giant nuclear furnace that lights our entire solar system, measures approximately 10,000 degrees Fahrenheit. This invisible barrier at the edge of our solar system is 5 times hotter than the surface of the sun. 5 times hotter at the edge of our solar system, in what we thought was cold, empty space. And here's the part that makes this even more puzzling. Voyager sailed right through it. Both spacecraft, decades-old technology designed in the 1970s, passed through this superheated region completely undamaged. No melting, no system failures, no thermal catastrophe. They just kept going, kept transmitting, kept sending data back home as if nothing had happened. How is that possible? How can something survive passing through a region 5 times hotter than the surface of the sun? The answer reveals something profound about the nature of space itself, something that challenges our everyday intuition about how the universe works. Here's where it gets fascinating. Temperature in space does not work like temperature here on Earth. Our everyday experience of heat involves contact, molecules bumping into each other, energy transferring through collision. When you touch a hot stove, billions upon billions of molecules in that metal surface slam into the molecules of your skin. That transfer of kinetic energy is what you experience as burning heat. The more molecules, the more collisions, the more heat transferred. But at the Heliopause, at that boundary Voyager crossed, the situation is completely different. The particle density out there is almost zero. We are talking about a few atoms per cubic centimeter, Not billions, not millions. A few. Yes, those particles are moving at incredible speeds. That is what creates the extreme temperature reading. Temperature, in physics terms, is really just a measure of how fast particles are moving. And these particles are screaming along at velocities that correspond to tens of thousands of degrees. But there are so few of them that they cannot transfer meaningful heat to anything they encounter. Think about it this way. Imagine being inside an oven. Normally, an oven at 500 degrees would cook you in minutes because trillions of air molecules are constantly colliding with your skin, transferring energy with every impact. Now imagine that same oven, same temperature, but with only 3 molecules inside. Those 3 molecules might be moving fast enough to register as 500 degrees on a thermometer. But with only 3 collisions happening instead of trillions, you would feel almost nothing, technically scorching, practically harmless. That is the heliopause. An invisible wall of incredibly fast-moving particles spread so thin that they pose no physical threat to anything passing through. NASA's Jet Propulsion Laboratory confirmed this in their December report. And I want to quote from it directly because precision matters here. The extreme energy recorded at the boundary does not threaten the probes due to near-vacuum conditions. The spacecraft continued to operate normally despite transit through regions of elevated particle velocity. Mystery solved, right? We understand why Voyager survived. Case closed? Not quite. Because here is the real mystery. The one that has physicists debating late into the night. The one that does not have a clean, satisfying answer yet. Why does this wall exist at all? The prevailing theory, the best explanation we currently have, goes something like this. Our sun is not just a ball of light and heat. It is a fountain, a constant, never-ending explosion in slow motion. A thermonuclear reactor that has been burning for 4.5 billion years and will continue burning for another 5 billion more. Every second of every day, our sun blasts out a stream of charged particles traveling at approximately 1 million miles per hour. We call this the solar wind. It is not wind in the way we experience wind on Earth. There are no air molecules being pushed around. It is a flood of protons and electrons and ionized atoms racing outward from the sun in all directions. A constant exhale from our star that never stops. For billions of miles, this solar wind dominates everything in its path. It pushes against anything it encounters. It shapes magnetic fields. It strips atmospheres from unprotected worlds. It influences the behavior of comets, blowing their tails away from the sun. Every planet in our solar system exists within this flow. Earth is bathed in it constantly. We are protected by our magnetic field, but we are swimming in the solar wind every moment of every day. We are all downstream from the sun, living within its constant exhalation. But eventually, far from home, far from the warmth and light we depend on, that wind runs into something equally powerful, the interstellar medium. This is the stuff between the stars. And calling it the stuff between the stars does not do it justice. This is material that has been accumulating in our galaxy for billions of years. Gas and plasma from ancient supernovae. The remnants of dead stars that lived their lives and exploded long before our sun even existed. Heavy elements forged in stellar cores and scattered across space when those cores collapsed. Hydrogen that has never been part of any star. Dust grains older than our solar system. Material that has been drifting through our galaxy since the Milky Way was young, slowly mixing and churning and filling the spaces between the points of light we see in the night sky. This interstellar medium has its own pressure, its own momentum, its own presence. It is not empty space. It is thin, incredibly thin, but it is not nothing. When these two forces collide, when the solar wind meets the interstellar medium, they do not pass through each other peacefully. They create a shockwave, a boundary, a zone of violent interaction where two realms meet and neither is willing to yield completely. The solar wind slams on the brakes. All that kinetic energy, all that momentum built up over billions of miles of acceleration has to go somewhere. Energy cannot be created or destroyed. It can only change form. And in this case, it converts to heat, extreme heat. Particle velocity increases dramatically at the collision zone as the energy of motion transforms into the energy of temperature. That is your 50,000 Kelvin wall, a cosmic traffic accident where our sun's breath crashes into the galaxy's atmosphere. A permanent collision happening continuously at the edge of our solar system, a boundary written in superheated particles. The theory is elegant. It makes physical sense. It accounts for the observations, but there are details that do not quite fit, measurements that raise more questions than they answer. Here is something else Voyager discovered, something that challenges what we thought we understood about the structure of our cosmic neighborhood. Scientists expected the magnetic field to change dramatically at the Heliopause. Think about magnetic fields as invisible lines of force stretching through space. Inside our solar system, these field lines run in specific directions, shaped and organized by our sun's powerful magnetic influence. The sun rotates, its magnetic field twists, and everything within the heliosphere follows that pattern. Outside, in interstellar space, the magnetic field should be completely different. It should be shaped by the galactic magnetic field, organized by forces that have nothing to do with our sun. Different origin, different structure, different orientation. So when Voyager crossed the boundary, researchers expected to see a dramatic flip. One moment, solar magnetic patterns. Next moment, galactic magnetic patterns. A clear transition, a distinct change. That is not what happened. Voyager 1 crossed the heliopause. The magnetic field stayed aligned. The orientation barely changed. Researchers waited for the flip. It never came. Then Voyager 2 crossed 6 years later at a completely different location, thousands of miles away from where its twin had passed. Scientists thought maybe Voyager 1 had just gotten lucky. Maybe it had crossed at an unusual spot. Voyager 2 would surely show the expected magnetic transition. Same result. The field lines matched. No dramatic flip. No clear transition. The magnetic orientation on both sides of the boundary was remarkably similar. According to NASA's 2019 JPL report, this was completely unexpected. The quote from the research team captures their surprise. "We did not anticipate this level of magnetic coherence across the heliopause boundary. The data suggests our models of the heliospheric termination require significant revision." What does this mean? What is the implication of matching magnetic fields on both sides of what should be a distinct boundary? It suggests that the heliopause is not a wall in the way we imagined. It is not a hard edge. It is permeable, a membrane rather than a barrier. Things leak through in both directions. Particles from inside our solar system escape into interstellar space. Cosmic rays from the galaxy penetrate into our sun's domain. The boundary breathes, it flexes, it allows exchange. Our solar system is not a sealed bubble. It is more like a cell with a semi-permeable membrane, constantly interacting with its environment, constantly exchanging material with the universe beyond. And here's the part that should give you chills if you really think about it. The heliopause moves. This boundary that defines the edge of our solar system, this wall of superheated particles, this transition zone between our cosmic home and interstellar space, it is not fixed in place. It expands and contracts in sync with our sun's 11-year activity cycle. Our sun does not burn at a constant rate. It pulses. It cycles. Approximately every 11 years, solar activity rises to a maximum, with more sunspots, more solar flares, more coronal mass ejections. Then it quiets down to a minimum. Fewer sunspots, calmer surface, weaker solar wind. When our star is active, when the solar wind is blowing strongest, the heliosphere expands. The bubble grows larger. The heliopause pushes farther out into interstellar space. When our star is quiet, when solar activity drops, the bubble shrinks. The interstellar medium pushes back. The boundary retreats closer to the sun. The wall is not fixed. It pulses. It breathes. It responds to our star's heartbeat. In a very real sense, the edge of our solar system is alive. Voyager 2 crossed the heliopause at 119 astronomical units from the sun. Voyager 1 crossed at 121 AU. That difference of 2 AU, roughly 186 million miles, is not random. It reflects the solar cycle. The boundary had physically shifted between their crossings because the sun's activity level had changed. We are not living inside a static structure. We are living inside something dynamic, something that breathes with our star's rhythm, something that has been pulsing for 4.5 billion years. And the Voyagers, those 48-year-old spacecraft that were only supposed to last 5 years, they are still out there, still watching, still measuring, still sending data home across billions of miles of void. In November of 2026, Voyager 1 will reach a milestone that no spacecraft has ever achieved. A milestone that puts everything we have discussed into humbling perspective. One light day. That is 16 billion miles from Earth, the distance where light itself, the fastest thing in the universe, takes 24 hours to make the journey. When Mission Control at JPL sends a command to Voyager 1 after November 2026, they will wait 48 hours for a response. 1 full day for the signal to travel out to the spacecraft. 1 full day for the answer to travel back to Earth. A simple question and answer will take 2 days. Real-time conversation becomes impossible. The delay is too long. Think about that. Voyager 1 will be so far away that even communicating at the speed of light, the cosmic speed limit, becomes impractical. The spacecraft many of you watched launch when Jimmy Carter was president, when disco was popular, when cell phones did not exist, will be operating in a realm so distant that the very concept of immediate communication breaks down. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, captured the significance of this moment beautifully. That kind of intergenerational effort on Voyager is really rewarding to see. I love these spacecraft. They are ambassadors for us here on Earth. Ambassadors. That word carries weight, because Voyager 1 and Voyager 2 are not just scientific instruments anymore. They have transcended their original purpose. They are messages in bottles thrown into the cosmic ocean, letters addressed to anyone who might find them, greetings from a small blue world to an infinite universe. Both spacecraft carry golden records. These are actual phonograph records, the kind your grandparents might have played music on, but made of gold-plated copper. The gold plating was chosen carefully. Gold does not corrode. Gold does not degrade. These records are designed to last 1 billion years in the vacuum of space, long after human civilization might be gone, long after the sun has changed and the Earth is unrecognizable. These golden discs will still exist, still carrying their messages, still waiting to be found. On those records are greetings in 55 human languages, every major language family represented, Mandarin and English and Arabic and Swahili and Hindi and dozens more. Some of the speakers who recorded those greetings have passed away now. Their voices are still out there, traveling through interstellar space, preserved forever. There is music from around the world encoded on the records. Chuck Berry singing Johnny B. Good, Bach's Brandenburg concertos, Beethoven's Fifth Symphony, traditional songs from cultures spanning the globe, Peruvian panpipes, Senegalese drums, Navajo night chant, the gamelan music of Indonesia, a sampler of human creativity chosen to represent the best of what we have created. There are images encoded on the records, 116 pictures showing what Earth looks like and who lives here, photographs of our planet from space, pictures of humans of different ages and ethnicities, images of our cities and our countryside, diagrams of human anatomy, pictures of animals and plants, a visual encyclopedia of life on Earth compressed onto a golden disc. The records include instructions for how to play them, written in a language of mathematics and science that any sufficiently advanced civilization should be able to decode, binary numbers showing the speed at which the record should spin, diagrams explaining how the stylus should contact the groove, everything a hypothetical alien being would need to hear the sounds of Earth from 1 billion years ago. Carl Sagan led the committee that chose what would go on those records. He and his team agonized over every selection. What represents humanity? What shows who we are at our best? What would we want another civilization to know about us? The responsibility was enormous. The opportunity was unique. They rose to the challenge. Will anyone ever find these records? Honestly, probably not. Space is vast beyond comprehension. The distances between stars are so enormous that even traveling for billions of years, the Voyagers will likely never pass close enough to another planetary system for anyone to notice them. The odds of another intelligence encountering a small spacecraft drifting through the darkness are essentially zero. Mathematics makes this clear. The universe is too big and the Voyagers are too small, but we sent them anyway. We included our music and our greetings and our pictures anyway, because that is who we are as a species. We hope. We reach out. We refuse to accept that we might be alone in the universe even when the evidence suggests we probably are. We throw messages into the void because the alternative, staying silent, accepting isolation, feels wrong to us at some fundamental level. Maybe that says something important about humanity. Maybe the Voyager Golden Records are as much about who we are as about who might find them. We are a species that hopes, a species that sends messages even when no one is listening, a species that refuses to give up on the possibility of connection. And in the meantime, while drifting toward forever, these ambassadors keep discovering things, keep surprising us, keep revealing that the universe is stranger and more wonderful than we imagined. That 50,000 Kelvin wall, that superheated boundary at the edge of our solar system, it raises questions we have not yet answered. Some scientists have suggested it might serve a purpose beyond simple physics. Could it act as a shield? The interstellar medium is full of cosmic radiation, high-energy particles from distant supernovae, gamma rays from catastrophic events halfway across the galaxy. Could the Heliopause, with its extreme particle velocities and complex dynamics, provide some protection? Could it deflect or absorb radiation that might otherwise make life on Earth impossible? We do not know. The data is not clear enough yet. But the question is worth asking. Others have proposed that there might be thousands of these boundaries throughout the galaxy. Every star with a stellar wind would create its own bubble, its own heliosphere, its own version of the wall that Voyager discovered. bubbles within bubbles within bubbles. The galaxy might be full of these structures, each star creating its own protected zone, its own domain carved out of the interstellar medium. If that is true, then what Voyager found is not unique to our sun. It is a universal phenomenon, a feature of how stars interact with their environment everywhere in the cosmos. Every solar system in the galaxy might have its own version of the heliopause, its own superheated boundary, its own membrane separating home from the infinite beyond. We are only beginning to understand what exists at the edge of our solar system. Voyager gave us our first direct measurements, our first actual data from that distant frontier. But there is so much more to learn, so many questions still unanswered, so many mysteries still waiting to be explored. The spacecraft that were supposed to last 5 years have now operated for nearly half a century. Their plutonium power sources are slowly dying. Each year, a little less electricity, a little less capability. By the mid-2030s, probably around 2035, Voyager 1 and Voyager 2 will finally fall silent. Their transmitters will shut down, their instruments will go dark. They will drift on forever, but they will stop talking to us. Until then, they keep working, keep measuring, keep sending data across billions of miles. Engineers at JPL carefully manage their dwindling power, shutting down non-essential systems to keep the most important instruments running as long as possible. Every watt counts. Every bit of data matters. These are the only eyes we have at the edge of the solar system. When they close, we will not have another mission capable of reaching those distances for decades. So we listen, we receive their transmissions, we analyze their data, we try to understand what they are telling us about the boundary of our cosmic home, a wall hotter than the surface of the sun, a membrane that breathes with our star's heartbeat, a boundary that is permeable, not solid. A region where our solar system meets the galaxy and the two shake hands across a zone of superheated chaos. Voyager showed us all of this. 2 small spacecraft launched before most people watching this were born, designed with technology less powerful than a modern calculator, built to last 5 years, still working after 48. So here is my question for you. That 50,000 Kelvin wall, that invisible boundary waiting at the edge of everything we know, do you think it is purely a natural phenomenon? A simple consequence of solar wind meeting interstellar medium? Or could it serve some purpose we have not yet discovered? Could there be a function to this structure beyond what physics alone can explain? Some researchers have speculated about the role of such boundaries in the development of life. Our solar system has been protected by this structure for billions of years. The heliopause has been filtering cosmic radiation, deflecting interstellar particles, maintaining a stable environment inside the bubble. Could this protection have been necessary for life to evolve on Earth? Would we exist if our solar system did not have this wall around it? And if you were on the Voyager team back in 1977, watching those rockets lift off from Cape Canaveral, tell me, did you ever imagine they would still be talking to us 48 years later? Did you ever dream that the spacecraft you built would rewrite our understanding of the solar system's edge? Did you ever think that your 5-year mission would become a 5-decade journey into the unknown? The universe keeps surprising us. Every time we think we understand it, we discover something that forces us to think again. That is the beauty of exploration. That is why we send spacecraft into the void, not because we know what we will find, but because we know we will find something. Voyager found a wall, a boundary, a transition zone between our little corner of the cosmos and everything else that exists. And in finding it, in measuring it, in trying to understand it, Voyager reminded us of something important. We are small. Our solar system is a tiny bubble in an ocean of stars, but we are curious. We build things that outlast us. We ask questions that take generations to answer. And sometimes, if we are patient enough, the universe whispers its secrets back to us. Thank you for watching. If this journey to the edge of the solar system resonated with you, consider subscribing. There is so much more to explore. More mysteries waiting in the data Voyager sends home. More questions we have not even thought to ask yet, and I want you to be here when we discover what it all means. Hit the notification bell so you do not miss the next chapter of this story, because the universe is still surprising us. Every day, more data comes in. Every week, researchers find something new in the observations. This story is not over. It is just beginning. Until next time, keep looking up, keep asking questions, keep wondering about what exists beyond the edge of everything we know. And remember that somewhere out there, 15.8 billion miles away, traveling through the darkness at 38,000 miles per hour, a spacecraft launched before many of you were born is still working, still listening, still measuring, still trying to tell us what exists at the boundary between our cosmic home and the infinite universe beyond. Voyager is still talking to us. The question is whether we are wise enough to listen, to really listen, to hear what it is trying to say about the edge of our solar system and our place in this vast, strange, wonderful cosmos. The 50,000 Kelvin wall is out there, invisible but real, waiting at the edge of everything we know, and thanks to two small spacecraft built in the 1970s, we know it exists. That knowledge changes things. It changes how we understand our solar system. It changes how we think about the boundaries between here and there. It reminds us that the universe is far stranger and more complex than we ever imagined. And if the edge of our own solar system can surprise us this much, imagine what else is waiting to be discovered. Imagine what other walls and boundaries and impossible structures exist throughout the cosmos. Imagine what we will find when we finally have the technology to explore further than Voyager has gone. The adventure continues, and I am glad you are here for it.